example where there are two masses 3 kg and 5 kg on a frictionless horizontal surface, and over there 20 Newton force is being applied in the horizontal direction, and these two blocks, they are connected by a rope which has a mass 2 kg and its length is 4 meter. Its length is 4 meter and the mass is 2 kg. We are supposed to find tension in the middle of this rope, that is at this length. So that 2 meter is here, 2 meter is here. We have to find the tension what is over here. So what we do is, that is as usual, what we do is we draw the force diagram, number one for this, the other is for this. Or force diagram, number one is isolate the body, diagrammatically isolate the body, it is diagrammatically only. Second is draw forces which are acting on that body, and third is apply Newton's second law, that is net force is equal to mass into action. These are three steps. So what we do is, over here when we apply a force of 20 Newton, we'll observe this system to be moving in this direction. There is no friction. Surfaces, they are frictionless. It is horizontal. So we'll see that this motion is purely going to be along the x-axis. So it means along the y-axis, the systems, they are not moving. So 30 Newton weight is going to be balanced by the normal reaction. Similarly, this 5 kg block will be applying a force onto this surface 50 Newton, and this will retort back, will apply a normal reaction onto that, which is going to be 50 Newton. So the forces, that is earth pull and normal reaction, they will get balanced, and as a result there is not going to be any motion along the y-axis. The unbalanced force is purely along the x-axis. So let's consider all the forces along the x-axis only. So what we do is, suppose this is 4 meter, middle means 2 meter here, 2 meter here. The mass of the rope is uniformly divided over its length. So it means if total is 4 meter has a mass of 2 kg, then 2 meter will have a mass of 1 kg. So 1 kg comes over here and 1 kg comes over here. Now as usual what we do is, when we draw the force diagram, this circle diagrammatically is cutting the string over here, this rope over here. So tension is this way. For this, it is this. We are not saying that is tension is same throughout the length of the rope. We are not saying it. Please do not misconstrue it as that is tension is same throughout the length of the rope. The tension in the rope will vary. It will change throughout its length, through its cross section when the system is accelerating. When we are saying T over here, it is at a particular cross section. We are saying that is tension at a particular cross section is opposite. To every reaction there is equal and opposite reaction. So when a force of 20 Newton is being applied onto it, every cross section pulls the next cross section with some force. So if this system through the rope at this cross section, these molecules at this cross section pull the molecules of the rope at this cross section with a force T, then the molecules at this cross section will pull back the molecules at this cross section of the rope with the same force, with the equal and opposite force. To every reaction there is equal and opposite reaction. So it is T. But the tension throughout every cross section, it will vary. Let's see that is what is the value of T. So obviously these are two kind of a coaches connected by a coupler or by a rod. So whatsoever is the acceleration of this block over here, the same acceleration is going to be of this block. Equation of this system is accelerating this way. Both the blocks, they have the same action. They are going together. Whatsoever the distance this covers, the same distance is covered by this. Whatsoever is the velocity of this, the same is velocity of this. Same is the velocity of rope. Whatsoever is the acceleration of this, the same is acceleration of this. So it is accelerating this way. So the force is 20 Newton this way, and we have to look within the circle only. 20 Newton is this way, T is this way. So net force is 20 minus T. That is, now we are talking of resultant force is equal to mass into action. Mass of what? Of the mass within this circle, that is 5 plus 1, 6 into A. For this, it is T is equal to 3 plus 1, 4 into A. If we add the two, 20 is equal to 10 into A comes out to be 2 meter per second square. Otherwise also, if you take this whole body as one body, then this circle, that is our free body circle, is not cutting this string anywhere. Diagrammatically it is not cutting. So these tensions, they become internal forces. So if we take this body, then the only external force is 20 Newton, and 20 Newton is responsible for accelerating all the mass, the whole mass within this circle, that is 5 plus 2 plus 3, that is 10 into A. So A comes out to be 2 meter per second square. It is the same thing. Now we have to find the tension. What is the tension at this particular cross section? So we can put the value of over here. So T comes out to be 4 into 2, that is 8 Newton. Now in the similar example, let's say we have 50 Newton force which are being applied this way. Two blocks 20 kg lying on a horizontal frictionless surface connected by a rope whose length is 10 meter, the mass is 10 kg. What is the tension at a length 3 meter from this block? So that is the question. So over here we observe that is 10 meter 10 kg. So it means if the length is 10 meter, the mass of the rope is 10 kg. That is mass per unit length. For 1 meter, it is 10 kg. 10 goes over here. That is 10 meters. So mass per unit length, it comes out to be 1 kg per meter. That is every meter has a mass of 1 kg. So obviously, that is when we talk about a 3 meter, it is 1 kg by 1 meter. So it is 1 kg per meter or per 1 meter into 3 meter, meter get cancelled. So that comes out to be 3 kg. So the mass of 3 meter is going to be 3 kg. Once again we see that is the blocks, they will be moving purely along the x-axis. There won't be any motion along the y-axis. So it means the forces along the y-axis, they are balanced. So let's talk about the forces along the x-axis. So once again we draw the circle, that is we are isolating the bodies for force diagram. So tension is over here. The direction of tension for this is this way, that is tension is always outwards. For this free body, tension is outward this way. For this free body, tension is outward this way. At one cross section, there is one tension. To every action, there is equal and opposite reaction. There are two bodies. We are taking this body as one. This is the other body. So whatsoever the force is being applied by this body onto this body, the same force will be applied by this body onto this body. To every action, there is equal, T equal, and opposite reaction. So the rest is easy. We know that is these two blocks, they will be going with the same acceleration. So now we apply the last step of force diagram, free body diagram, that is F is equal to ma. This is going this way. So equation comes out to be 50 minus T is equal to mass. Mass is what? This is 3 meter. So this was obviously that is 3 kg mass is this. So this is 7 meter. So this is 7 kg. So total mass within this is 50 minus T is the net force is equal to mass 20 plus 7, 27 into A. The equation comes out to be like this. And equation for this is, that is what is the force which is acting along the x-axis? It is the T is the only force. So T is equal to mass 20 plus 3, 23 into A. You can add the two, that is 50 minus T plus T, they get cancelled. 23 plus 27, that is once again it is 50 into A. A comes out to be 1 meter per second square. So you can put it over here. So T comes out to be 23 into A, that is 23 Newton. That is the value of tension at this cross section. In case of idle string which is massless, inextensible, the tension remains same throughout its length. Like over here, if we have two masses 3 kg and 2 kg on a horizontal frictionless surface, and from here 10 Newton is being applied. So we know that is how to find the tension. We can easily find it. But why the tension? It has to be same throughout the length of the string. This is massless idle string, inextensible string. So let's assume that is tension is varying. Let's assume it otherwise, that is tension is varying throughout its length. So what we do is we draw a force diagram for this section of string. We say that is, let's say the tension is different at the different cross sections. So over here, let's take it as T dash, over here let's take it as T. So now our free body is this length of the string, we have taken it as a free body, and we are following all the steps which we had done earlier in force diagram or for drawing the free body diagram. So first is we have drawn the circle on our free body, then is we see what are the direction of the forces and what are the forces acting on it. So there is only one force, it doesn't have any weight, so weight mg will not be there. It is only that is tension is always away from the body. So T dash is here, T is here. We have assumed that is, let's say there are two tensions at the different cross sections. Now whatsoever is the acceleration of the whole system, this will also be going in this direction with the acceleration A. So if we write the equation of this, that is F is equal to ma. Now we coming to the last step, that is net force is equal to mass into acceleration. So over here net or resultant force is T dash is this way, T is in this direction is equal to mass. This is net force. What is the mass of this? This is idle string. Idle string has a mass 0. So 0 into A, so that means T dash is equal to T. So a string has a same value of tension throughout its length. So now the tension is same throughout the length of a string, idle string, and we have also done, that is, the tension in a rope is varying. Suppose the system is accelerating, and then the tension across different cross sections is going to be different. But what if there is a rope but the system is not accelerating, like in this case? Over here 20 Newton force is being applied here. This is 15 kg, 5 kg, and there are two ropes of any mass, any length. So surfaces, they are frictionless and horizontal. Now the question is, in such a case, whether the tension will be varying throughout the length of the rope or it will be same. Let's see. So we see 20 Newton is over here. This will try to pull the system over here, but this is tied to a wall or to fixed support which can't move. So the system is stationary. When the system is stationary, it means the acceleration of this is also equal to 0 and acceleration of this is also equal to 0. Now if we take this as free body, so now this is my wish, that is, I can cut the, diagrammatically I can cut the string here also, here also, here also, anywhere. Acceleration is equal to 0, so T is over here, T is in this direction, acceleration is equal to 0, it means net force has to be equal to 0. So 20 Newton it has to be equal to T, so 20 Newton it has to be T. And in case I take this bigger circle, then for this 20 Newton is here. Now we have taken a bigger circle so that a bigger mass of rope is included in the free body. And what we are doing is, we are trying to find a tension at a different cross section, and we'll see, that is, whether the tension comes out to be same at the different cross section, tension comes out to be same as the earlier tension or not. So once again for this, it is acceleration is equal to 0. Acceleration is equal to 0, it means that is once again T dash, it has to be equal to 20 Newton. So in this case, the tension is same throughout the length when it is not accelerating. So in all the cases, wherever you have a string, wherever you have a rope, you will accordingly, you will use the concept to find the tension at the appropriate length.